Back, everybody, to another edition of No Here, No Problem. Rosenwald here, talking about Unit 5, Chapter 1, or I'm sorry, Unit 5, Section 1, excuse me. And in this section, we're going to be starting on trig proofs. And as I told you guys in class numerous times, this is one of those things where you're going to struggle. You're going to definitely struggle, but the best way to actually get better at these and more proficient is to just try things. You try things, you experiment, you fail, you do it, you try again, and you just keep persevering on. You'll get the hang of it. You'll start to see patterns as we kind of work through things. But I'm going to try to give you guys some tidbits along the way that are going to help guide you a little bit and keep you on the right track as far as like how to navigate some of these problems. If at some point you get stuck, go back, watch it again. Don't be afraid to pause it, try something on your own, and just to see where like you go with it, and then hit play just to kind of see how I do it afterwards. Okay. In this section, I'm going to be giving you guys a cheat sheets along the way to keep track of all the different identities, but I am going to talk to you a little bit about where each one of these identities comes from. So it's not just like, here's a bunch of identities, okay? The first identities that we're going to reference here are these trig identities that are the reciprocal ones. We've talked about those in the past extensively, so you should remember that, you know, cosecant is 1 over sine, secant is 1 over cosine, and so on and so forth. The ones that are really going to jump out and be important to you should be these right here, tangent and cotangent. It's because these are the ones that we can use sine and cosine and sine as, you know, fractions and reciprocals of each other. They're going to surface pretty frequently as we're doing these problems, okay? In these next section here, you're going to see there's a couple of them that are really important. The Pythagorean identities, these things are going to be everywhere. We're going to see them all the time. And then the cofunction identities, we're going to see those occasionally. And then we'll see the odd-even identities. Now, I do want to take a couple minutes to give you some clues as to how to work through these problems, but also where do these actually come from, okay? So let me go ahead and take myself, I'm going to shrink myself down and get me out of the way as usual, and let's get started here, all right? So first and foremost, when you're doing these, a couple things to remember is try to factor whenever you can, okay? We did an algebra and trigonometry review before we started this unit, so that a lot of that entailed factoring. So whenever you're doing problems and you think you can factor, try it, see what happens. It might work out, it might not. In terms of factoring, look for the difference of squares. I'll show you why in a moment, why this surfaces pretty frequently, but it actually is linked in with the Pythagorean identities that we see down here, okay? And then lastly, whenever you're in doubt, whenever you're just stuck and you're not really sure where to go with the problem, try switching things to sine and cosine and just see what happens, okay? All right, so let's jump in here. Let's jump into what we should know and remember from these problems. So when we talked about, when we started this trig unit, we talked about the unit circle extensively, and it's the unit circle that actually leads to our identities for us, okay? If I was to draw in a right triangle here, and I know that going to the right in this is x, going up is y, and that if it's a unit circle that this is going to be equal to 1, right? Well, we should remember that the sine of theta is equal to y over 1, which means that the sine of theta is just equal to your y value, okay? So keep that in mind for a moment. Now let's go ahead and do the second part, which is cosine, that the cosine of theta is equal to x over 1, which means that cosine of theta is just equal to your x value, right? This is stuff we learned already when we first started talking about all the trig stuff. Now let's talk about what you've learned way in the past, the Pythagorean theorem. What we know is that x squared plus y squared is equal to 1, because c squared. And if we do some basic substitution, knowing that x and y are cosine and sine, what I could do is a basic substitution that says that cosine squared x, and they use x instead of theta, same difference, but I'll go ahead and use theta in this instance, plus sine squared theta is equal to 1. And that's our first identity that we have called the Pythagorean identity, which is over here on the left side, okay? This is going to surface very frequently, extremely frequently, so be on the lookout. And then we're very lazy. We are extremely lazy when it comes to writing these, so we write c squared plus s squared is going to equal to 1. Well, how do we get those other identities, right? This all is really simple. It, just ties in sine and cosine. How do I get tangents and secants and cotangents and cosecants? Well, we can play around with these and make some simple changes. If I took my c squared and I divided it by c squared, and I divide this by c squared, and I divide the right side by c squared, what ends up happening is we have c squared divided by c squared, which is equal to 1. We have sine squared, or s squared, divided by c squared. We'll go back to your identities up here. S divided by c right here is the same as tangent. So we have 1 plus tangent squared of theta. And then we have 1 over cosine squared, which we know is secant squared theta. Okay? So that's one of our identities. Let's do it again. If I cosine squared plus sine squared is equal to 1, and instead of me dividing everything by c squared, what if I divided by s squared? What we're going to end up with is a 1 right here for the s squared. 1 over sine squared is cosecant squared. And then we have cosine over sine, which goes back to this identity of cotangent. And we know then that this is going to be cotangent squared theta plus 1 is equal to cosecant squared theta. So I said to you guys, one of the clues when we're working through these is that the difference of squares is going to happen pretty frequently. Well, why is that? Well, if we look at this c squared plus s squared and it's equal to 1, if I take and move one of these, I end up with 1 minus s squared. And you can see we have a difference of squares taking place right here. So if that's the case, we can say that that 1 minus s and 1 plus s is the same thing as a c squared. Okay, that difference of squares. In addition, one of the things to notice is a lot of times people don't like the way that this looks. And so you're allowed to take that and switch it around if you'd like. You can actually make this into a negative s squared and a positive 1. And then what happens is I can factor out a negative 1, and we're going to be left with s squared minus 1, which means that we have c squared is going to equal negative 1 times s minus 1 and s plus 1. So these are just some things that you could do to kind of play around with the problem to get it to look the way you want. All right. These cofunction identities, these just come from the fact that we know that when we look at sine and cosine, that they're really just a phase shift away from each other. So if I was to look at a sine curve, we know that the sine curve looks like this. And if I looked at a cosine curve, we know that the curve looks like this. And what ends up happening is if I was to take one of these graphs and go ahead and shift it, if I took the sine and shifted it, what's going to happen is, whoops, I highlighted too much stuff there. If I took this and I shifted it, I just do a phase shift, you can see it ends up being the exact same curve. So that's all it says, is that when we're looking at sine and cosine, if I simply do a phase shift of my sine by pi over 2, it ends up equaling my cosine. So the picture we have. And it's the same thing for the other functions that are there. The last thing that we're going to talk about here is the even-odd identities. And what this one says is, if you're looking at this, I've got a sine curve that looks like this, right? And it comes back over in this direction. And if I was to say, all right, well, take the opposite x value. So let's just say I looked right here at this value, which we know is at pi over 2. And if I say, well, what's the opposite x value? Well, go the other direction. Instead of going right pi over 2, I go to left pi over 2. And what happens is we have a negative on the outside. Remember, this is saying the negative f of x, which is saying the opposite y value. So instead of me going up to a 1 right here to pi over 2, 1, I end up with another value over here, which is at negative pi over 2, negative 1. So that's all these odd even identities do for us, is just expose like what happens if I use the opposite x value. So if I was to look at like a cosine function and say the opposite x value, well, if I go ahead and look at a cosine function, we know that the graph generally looks like this, right? And it's the same thing over here. And so if I said, let's put in the opposite x value, well, if I went to this spot right here, the opposite x value will take me back to the left side, and it's the exact same y value, so nothing changes there, okay? So that's all these are. It's just implementing the rules that we see from the graphs themselves. But let's get started. Let's jump in, okay? So in terms of example number 1, what we're looking at is there's 2 ways that we can go about doing this simple problem here. There's an old school way that we used to do this, and then there's a new school way, which is using the formulas that we are given in this section. So let's talk the old school way before we actually dive into anything, all right? First thing we recognize is they're asking us to find the sine and cosine if the tangent of theta is equal to 3. Well, tangent of theta, if you remember, is really just opposite over adjacent. So that means we have 3 divided by 1. If we look at where to draw that in our circle here, we know that all functions are positive in the first and the, in the first quadrant. Tangent is positive in the first and the third quadrant, okay? When we're looking at the second part of this, which says that cosine is less than 0, what we're saying is that this is a negative, that it's got to be a negative, so cosine is going to be a negative value. Well, cosine is positive in the first and the fourth quadrants. That means we're looking at this quadrant and this quadrant. The overlap that happens in this is in the third quadrant. So let's go ahead and draw in our triangle here. We're going to have a -3. A -1 and then a -3. They're both negative because we go left and then down. Use the Pythagorean theorem to find that last side, and we end up with a √10. So if I was to say, all right, based on the scenario, what's the sign of this? We're going to go ahead and use the opposite, which is -3, over 10. So the sign of this is going to be -3 over √10. If I said, what's the cosine? We're going to use the adjacent divided by the hypotenuse, which will be -1 over √10. And that's it. That's as simple as it is if we go the old school method. Now, new school method, let's talk about what we actually do know. I'm given a tangent. So if I look at my identities up here, we have one that we can work with, which is this right here. Okay? And so let's use that. Whoops. We know that if I use 1 plus tangent squared, it's going to equal secant squared, excuse me, theta. Sorry. And so if I look at the fact that we know that tangent is equal to 3, that means we're going to have 1 plus 3 squared is equal to secant squared, which means that we have 1 plus 9 is equal to secant squared, which means that we have 10 is equal to secant squared. If I want to get rid of that square, I go ahead and take the square root of both sides, and we end up with secant of theta is equal to positive or negative. Believe it or not, it's actually positive negative √10. But the issue is that we know in this problem that cosine has to be negative, and we know that secant is the reciprocal of cosine. So if my cosine has to be negative, that means that secant also has to be negative. And so that means instead of us using positive negative, we just say negative √10. So if I say, all right, well, what's the cosine of this situation? We know that cosine is just the reciprocal of this, okay? So then the last part of this is, well, how do I find the sine if I know the cosine and the tangent? Well, we have a formula. We know that the tangent of theta is equal to sine of theta over the cosine of theta. I know that tangent is equal to 3 in this problem because that was given to me. I now know that cosine is equal to -1 over √10, and I still have to find sine. So if I go ahead and multiply both sides by -1 over √10, we get -3 over √10 is equal to the sine of theta. So this new method is more just a straightforward algebra conceptual thought process versus the first method, which is more you have to understand and know where everything is related within the unit circle itself. All right? All right, let's jump down to some more challenging questions. This is one we're probably going to see on the test here. They're asking us to find the cosine of theta. They're telling us that the cosine of theta is equal to 0.34. They want us to find the sine of theta minus pi over 2. The problem is that when I look at this identity, it looks very similar to another identity that we have up above. That identity is this one right here. Now you can see when you look at these are very similar, but they're slightly switched around. And if you think back to what I said earlier, that if we ever want to take and rearrange things, all you got to do is factor out a negative, then that's going to help us with this problem, okay? Let's see what we can work out here. So let's start with what we know. We know from our identity up above, so this is what we know, that the sine of pi over 2 minus theta is equal to the cosine of theta. I don't like the order of that. So what if I took and rearranged the theta minus pi over 2 and I factored out a negative to get that rearrangement going on? Okay, we can do that because I could factor out a -1 and it keeps everything the same. It just switches things around. Well, that negative that's in front looks very much like another identity that we have up above. If I look at this right here and I look at this identity up at the top here, you can see that these are the same identities going on here. That when we have a negative on the inside, that negative can actually get moved to the outside. And so we end up with this, okay? And so this is the even odd identity that we just worked with at the top there. Well, that negative that's in the front, I can actually move that over to the other side, which means that we have the opposite of the cosine of theta. And if we think about what we know that the cosine of theta is equal to 0.34. So that means if I throw that over here, my answer would just end up being a negative 0.34. And that's what the sine of theta minus pi over 2 is. Okay. All right, let's get some easier questions. So all these we're just simplifying until we actually see the direction where it says to solve. So simplifying means we're just simplifying, making it look easier. Like if I said simplify 5 plus 3, you would say it's 8. We're going to take each one of these and we're going to simplify them using rules that we are given. Now, we are lazy. Let's be lazy when it comes to writing these. When I see a c cubed and a c and an s squared, let's go ahead and write it as a c cubed and c and s squared. And I have a sneeze coming. No sneeze, false alarm. All right, so one of the clues for you to know is this. A lot of times when we're simplifying these, if we're simplifying, not trying to prove, if we're trying to simplify, we don't want to have a 3 in here. A 3 is considered way too big in these problems, and we can work with it if we had smaller ones. So factor out a c, and if we take out that c, we're left with c times c squared plus s squared. Now this identity right here is one that we should recognize. I mentioned this before, that this is actually related to our Pythagorean identity. If we know that c squared plus s squared is equal to a 1, then in place of my c squared and s squared, I'm going to put a 1. So that means we have c times 1, which leads just equal to c, or cosine. All right. Let's take a look at another example where we're going to be simplifying. I don't like the way this one is written, the secant of x plus 1, the way it's all written horizontally, so I'm going to rewrite it so it's actually vertically. So if we look at the top here, we have the secant of x plus 1 and the secant of x minus 1. And what I did was I multiplied that together. That's that difference of squares. Secant of x plus 1 doesn't really help me anywhere in my problems here, right? If we look at my identities, that's nowhere to be found. But the secant x squared minus 1, it actually is somewhere to be found. Because when I look at this, this is one of my Pythagorean identities. That if I go ahead and take my 1 and I move it to the right, if I take this 1 and move it over here, we end up with the tangent squared of x. Okay? And so I can use this. I now know that this is equal to t squared instead of my secant squared x minus 1. All right, well, what about that sine squared? It just carries through. There's nothing to do with it. Can we simplify it a little bit further, though? Well, that tangent squared can actually be written as a sine squared over cosine squared. All right? And because it doesn't feel like we're simplified all the way when I have a tangent squared over sine squared. So let's see if we can go a little further. Tangent squared is the same as sine squared over cosine squared, and that sine squared is still the same. If I rewrite the way that this is written, this right here is saying this portion divided by that bottom portion, right? And so if we look at that, I could take that s squared over c squared and divide it by s squared, which is the same as multiplying by the reciprocal. So we still have 1 over s squared. What happens is my s squares will cancel each other out, and we're going to be left with a 1 over c squared. Well, 1 over c is the same as just secant, and that's the most simplified form that we can get to. All right? All right, one more simplifying, then we're going to do 2 solving problems and we're done with these notes, okay? So first thing I'm going to do is I'm going to go ahead and I'm going to simplify this by first getting rid of the cosine and sines and just writing c's and s's, okay? So I took c over 1 minus s, and then I did minus s over c. And when we're doing these kind of problems, when you see fractions where there's 2 different parts here, anytime you see a part here and a part here and there's subtraction in the middle, this is a binomial, and generally in simplified form, binomials are actually put together to be a monomial, so there's just one term. Well, how do I do this? How do I get fractions to be exactly the same so that we can put them together? Well, in order to do that, we usually get a common denominator. If we look at this denominator right here, there's a c missing right here. And if we look at the denominator on the right side, there's a 1 minus s missing over here. So what that says is that, well, if I'm going to get the denominators to be the same, I got to do the same to the top as I do to the bottom. So let's take this and move it over into the problem here so that we have those c's there. And let's go ahead and take this and we'll move this over so that this is now part of the problem as well. Now my denominators are the same. Well, how does this help me? Well, if I put the problem together with the numerator, this is what we end up with. We have a c squared minus s squared. All right. Now, I'm not multiplying out the denominator. You'll see why in a second. This is one of the things you start to recognize when you practice these a lot. Okay. But if I take the numerator and go ahead and distribute this negative to everything, that negative, you got to be very careful with it, is going to make it into a negative s and a positive s squared. Well, if we look carefully in here, we have now a c squared and an s squared. What is that? Bam. It's your Pythagorean identity. That c squared and that s squared is the same as the c squared s squared right here, which we know is just equal to a 1. So let's replace that with a 1. That means that we end up with a 1 minus s over c times 1 minus s. And now because I have the same thing on the top and the bottom, I can go ahead and get rid of my 1 minus s's, and we're left with a 1 over c. And 1 over c is the same as a secant of x. That's our simplified answer here, okay? All right, we're going to do 2 questions with solving, and I highly recommend that you actually have your unit circle out as we kind of work through these, okay? So first thing I want you to know is we're looking for the answers for this when we're solving. We're looking for answers, all the values that lie from 0 to 2 pi. And you'll notice right here that we use a parenthesis around 2 pi, meaning we don't include 2 pi. And that's because on the unit circle, 0 and 2 pi are at the exact same location, so it'd be redundant to use 2 pi as well. There's something else that we have to recognize here, this cosine of x. Do you see how the cosine of x in this is at the denominator? Anytime we're doing a solving problem and we say that there's a denominator, there's the domain restriction. The domain restriction here is very simple. That cosine of x cannot equal 0. It can't equal 0 because if it did equal 0, the whole problem becomes undefined. Well, where is cosine of x equal to 0? Let's look at our unit circle. We know that the cosine of x is our x value. And where do we have an x value equal to 0? That's right here at 0, 1. I'm sorry, at pi over 2. It's 0, 1. And then we look here, we get at 0, negative 1 is the coordinate at 3 pi over 2. So looking at this then, we're going to go ahead and say that theta, or x, cannot equal pi over 2. And it cannot equal 3 pi over 2 either. Whoops, 3 pi over 2. So that's just to talk about the domain restrictions. Let's worry about how to actually go about solving this, all right? A lot of ways we can go about this. I'm just going to try to keep everything as simple as possible, all right? So first thing, every time we're doing any of these problems, you have to set them equal to 0. That's how you solve these problems, is everything has to be equal to 0. So let's go ahead and take our problem. We have an s cubed over c is going to, we're going to subtract tangent of x, and that's going to be equal to 0. Now, it doesn't help me to have 2 separate fractions when we're working here. We have to put these fractions together. So that means that I need that c that's in the left side to work with the tangent portion, and we know the tangent is the same as sine over cosine. Let's put these together. We now have s cubed minus c s over c, all right? And then when we look at this, we have s cubed minus s. I could factor one of these s's out, and we're going to be left with s times s squared minus 1 over c. And we get is equal to 0. All right. Now, when we look at our Pythagorean identities, we should recognize sine squared minus 1. We know that that's actually equal to negative c squared. Okay, from doing the s squared plus c squared is equal to 1. We get that s squared minus 1, if I move this way, and I move the c squared over, is going to be equal to negative c squared. So we have s times negative c squared divided by c is equal to 0. I can go ahead and get rid of one of my c values here, and what we're left with is a negative sine of cosine of, I'm sorry, I left out the thetas there, I apologize. So we end up with a sine theta, negative cosine theta, and it's going to equal 0. And so now we can use a property called the zero product rule. What that says is that if this is equal to a 0 right here, 0 times this is going to equal 0. So we just solve for when that is equal to 0. And it also says that, well, if this is equal to 0 times this, that's going to equal to 0. So when does that second part equal to 0? This relates back to like just very basic stuff. Like if I gave you x minus 2 times x plus 3 and I said solve this, you would set x minus 2 equal to 0, and you would set x plus 3 is equal to 0. It's the same premise, okay? All right, so let's solve for each one of these. When is the sine of theta equal to 0? And when is the negative cosine of theta equal to 0? Well, look at your unit circle. The sine of theta, which is the y value, is equal to 0 at this location right here, which is at 0. And then right here, when it's equal to pi, is the other location. All right. So that means that we get that theta in this problem is going to equal to 0 and to pi. And then this other one, we discussed this one. Cosine can't equal 0. And so there's nothing to worry about for this because of the domain restrictions. Excuse me. So then our answer for this is 0 and pi. All right, we have one more question. This one's not too difficult. It's just that it has a detail that you have to pay attention to. All solutions. What does that mean when we say all solutions? The distinct difference here is that we have 0 to 2 pi for this one. We don't have that restriction on this problem. So the answer is going to be just slightly different. All right. Let's get there in a second, but let's worry about how to solve this first. So when I look at this one, this is 2s squared plus s is equal to 1. It's a quadratic. Everything has to be equal to 0 in order to solve this. So we're going to have 2s squared plus s minus 1 is going to equal to 0. If I factor that, we get 2s and s. Those are the only factors of that first spot there. So they have to be a 2 and a 1. The only factors of 1 are 1 and 1. And then the values that we're going to use for the middle are going to have to be, and this is where you have to get better about guess and check. They can't both be pluses because of the fact that we have a negative here. They can't both be negatives because of the fact that we have a negative here. One of them has to be positive and one of them has to be negative. I need to put a positive here and a negative here because this gives me a positive 2. And then multiplying this out, that's going to give me a negative 1. And 2 minus 1 gives me a positive 1. If we solve this, we're going to get s is equal to 1/2. I think my pen just died. Hang on. Oh, no. S, or it's dying. It is dying. We're getting close. Here, I'm just going to disconnect it. All right. So for this first part, we get that s is equal to 1/2. And then for that's terrible right in there. Sorry, I don't have my stylus anymore. It just died on me. And then for the second one, we get s is equal to negative 1. So this is where we have to look at the unit circle. Where do we have a sine value equal to 1/2? And that's where do we have a y value equal to 1/2? That happens right here at pi over 6. And then the other one happens right over here at 5 pi over 6. And then we said, well, when is sine equal to negative 1? That happens right here at 3 pi over 2. That's where that y value is a negative 1 there. All right. So we have three answers for this. That the sine of theta, that x is going to equal, we just said pi over 6. We said 5 pi over 6. And then we said 3 pi over 2. Okay. Now these are three answers, but it's not all solutions. The all solutions part is just one minor addition to the problem here. We know that when we look at sine, this is what the graph looks like, right? And it goes forever in each direction. If I was to say to you, when is the sine of theta equal to 1/2? Well, 1/2 happens like right here, and 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 right here. And technically, there are an infinite number of solutions for this, right? So how do I take care of all of the solutions? Well, what's the period of sine? It's 2 pi. And so if I looked at one of my answers that's on here, this answer right here, the next one that's in the same location is all the way over here, which is 2 pi away. And if I was to go the other direction, back to this one, and I wanted to get back to the left, that is 2 pi away. And so what we're going to do is we're going to account for all solutions by saying, let's add or subtract increments of 2 pi. And so what that looks like is we're adding or subtracting 2 pi, adding or subtracting 2 pi, adding or subtracting 2 pi. But then there's one last modification that we do here. Adding or subtracting 2 pi would just take me one to the right and one to the left. I want to go indefinitely to the right and indefinitely to the left. And so what we do is we add on a k value here, where k just represents how many times to the right you want to go. You want to go 1 time, 4 times, 10 times, however many you want, that's how many to the right or left that you're going to go. Okay? So this concludes section 5.1 notes. The homework is pretty extensive, but I recommend you try to do every problem and then ask for any help that you have. But practice makes perfect with these, everybody. And don't be afraid to talk to people and bounce ideas off. As you can see, these are kind of difficult problems, but you do get the hang of them, okay? Until the next time, you guys take care, be safe, be respectful, and be responsible. Don't forget to like and subscribe to my channel, and you have a wonderful day.